what today would be, and that is we've got two things to go through as far as material to kind of complete the kind of course content. The first is to jack up the frequencies and look at ground penetrating radar, and then the second is to look at dispersive properties, namely electrical conductivity, and that means that we're talking about induced polarization. After that, that would be a logical place for people here to present things, because Sergio has got a problem that is connected to pyrite, which is chargeable. So maybe there's some connections there. Maybe there is, maybe there isn't. Jensen, you might want to talk just a little bit about like the problem that you're doing. And I don't know if there's anybody else that just wants to offer some suggestions or have some questions, but let's do that right after coffee. I think we should be able to just do the GPR and the induced polarization before lunch, and then right after lunch we could have these other presentations, and then yeah, we'd like to kind of open up and ask you a couple of questions about the use of the apps. Let's just spend a bit of time just kind of reconnecting with the material and just having an attempt to do something and just to ask or answer a couple of questions. And then, yeah, then we just round it out, talk just a bit about the future. We just have some summary slides and tell you, review a little bit about what we did in the course, but just talk a little bit about what the future might hold, and yeah, then that would be it. So if that sounds okay, I think let's plan to do that. But we're completely flexible. I mean, if there's something that comes up that seems like that's really of interest to you and you want to discuss that, do not hesitate to ask. Oh, thank you.
The slides will be up in a minute. Sorry, I didn't do this last night.
Well, she was going to do it, but then she ended up at this place called St. Arnold. And then having all that Santa beer. Santa? So what was that? It was quite good. Santos. That's what happens. You bring your colleagues to Houston. Just change. Okay. Ground penetrating radar. How many people have somehow been in contact with somebody that's done ground penetrating radar or seen a radar unit? Or
I saw it once. It's actually a couple of decades ago.
Decades. that's
When I was at the college.
Yeah, life's like that, right? You start to recount things and you think, now you're starting to go, oh yeah, that was a couple of decades ago. It's a long time. Okay.
Getting old.
So what's the motivation for this? Again, there's a whole bunch of problems that exist at different scales, but there's sinkholes. Brazil, you must have lots of places where you got limestone cave sinkholes, right? Saltwater intrusions, smaller scale stuff like underground storage tanks, archaeology, rock glaciers, a whole bunch of potential applications.
Jail tunnels.
Pardon me?
Jail tunnels.
Jail tunnels, right, exactly. So what I want to do is just we're not going to go into this in depth, but just kind of give you an overview, the basic experiment, physical properties, talk about physics, data processing. I want to show you one example of how it might be used in vehicles, and yeah, maybe I'll talk about the rock glacier too. So here's the basic experiment, and the thing about GPR is that for anybody who's done seismic, it's like, okay, I understand completely what's going on. We got a transmitter. It gives off a pulse, and that pulse goes down, gets reflected back off, and goes back to receiver, and then can go off of multiple interfaces, and everything can kind of be in one box. You've got your data sampler here, storage. There's generally some signal processing that's going on, and there's probably even display. So as you're walking along, you've got a unit that is basically displaying your radiograms as you travel. So what's our equations? Nothing has changed. The only thing that changes is we're going to put this term in here, the time derivative of the electric displacement. And the electric displacement is the product of the electric field and the electrical permittivity. So now we need another physical property, electrical permittivity. So far we've seen conductivity, magnetic permeability, though we haven't talked about that much. We've got epsilon. This slide, again, we saw before, we had Maxwell's equations. We could combine them into a second order equation. When we were doing this earlier, we got rid of this term. This is a propagation term. This is a diffusion term. And we got rid of this wave propagation, and we looked at just this. And we talked about that as being the quasi-static. Now, we're going to be interested in putting both terms in.
So may I ask, like, why do you put this term back for the GPR system? Because of the frequency we use?
Mm-hmm. Right. So let's see. It'll come up. It's on a slide here someplace. But basically, when it's the ratio, and you can kind of see it here. It's when this term actually gets larger than this term. So what have we got? We've got an omega squared mu epsilon, and we got an omega mu sigma. So if you're going to look at the ratio of these two guys, then the mu is going to cancel. So you got omega epsilon controlling the diffusion term, and you got you got sigma controlling this. So one of the omegas cancel out, so you got omega epsilon against sigma. So now if you look at the ratio of those, is if omega epsilon upon sigma is really small, then you forget this term. If it's really large, you've got to keep it in. So the physical properties is really, it really is the electrical permittivity, but we always normalize that to what the permittivity of free space is. So that means that we're looking at epsilon sub r, the relative dielectric permittivity, or sometimes it's called the dielectric constant. So that's where that comes in. Air is 1 because we've taken the ratio. Water is 80, and it doesn't matter whether it's fresh or salt. And then you've got saturated sands. Well, saturated sands have a lot of water content, so they can get high. And you've got granites or shales have a low value. But basically, things change between 1 and 80. So they're not changing many orders of magnitude like they did with conductivity between 1 and 80. The other thing is that as the wave travels through here, they're going to be traveling at meters per nanosecond, because we're basically talking about stuff traveling at the speed of light. And now you're going to look at wave propagation speeds. There's also, we're going to need the electrical conductivity because that's going to control how much things decay. So still electromagnetic wave, it's still going to decay. And perhaps this bottom, or the final column is of interest, and it has to do with attenuation. If you have fresh water, for instance, then you could think about the electromagnetic, or this propagating in, maybe a couple hundred meters. On the other hand, if you have seawater, which is highly conductive, now you've got really large attenuation, it only goes in maybe 10 centimeters. So the depth of penetration is going to depend upon the electrical conductivity.
So I have a question about the velocity. Basically, you're showing the equation there, the velocity is the C divided by the relative conductivity. So the freshwater and seawater has the same dietary constant, but why their average velocity are different for the freshwater and seawater?
That's a very good question. Huh, okay.
What was the question though?
Oh, so we've got the velocity is c by root epsilon, but epsilon is 80 for both of these. We have different numbers.
So
Yeah.
C over epsilon, root epsilon is the first order.
Yeah.
The conductivity actually does come into that.
Yeah.
Well, like that's when we're actually ignoring EM induction, right? This velocity equation. So when you're taking account EM induction part, that now conductivity comes in. So
Okay.
you can show that now.
Yeah, that's what I was going to show the. Okay, listen. But for skin depth, we have an app, and here's an image from it. So I think this is the important part for the skin depth, and that is that. Remember when we had the quasi-static, so omega epsilon was less than sigma. Then this is what we had: 500 root, basically rho upon f. And if we look at skin depth attenuation, skin depth against frequency here, in that quasi-static regime, it's basically following this. Once you get to the point where that no longer occurs, then you see that the skin depth no longer changes. So now it's going to propagate, okay, without losing EM attenuation in here, and it can, so it no longer has that frequency dependent, but it still is attenuating according to this. So you still have a skin depth that depends upon the square root of a dielectric constant. So if we look at an electric dipole in a whole space, we did that yesterday, and if we crank up the frequency, then you start to see things that are really pretty interesting, right? Because you've got current that is sort of going around like this, and then you've got changes, it's propagating out, and now you've got a maximum here, another amplitude here, another amplitude. If you go even to higher frequencies, you can just see, like if you plotted the amplitude of what is going on this line here, it would be up, down, up, down, up, down. So you actually see the different wavelengths, and you can verify for yourself. You can take a look, because you can count what the period. You can look at what the period thousands of records and then gradually up and increase that signal to noise. So 5 stacks, something looks like that.
Similar to a GeoSci.xyz.
Yeah, exactly.
So in this case, I will assume because of the attenuation, you will have higher amplitude at early time and lower amplitude at later time. But why didn't show in this case?
Just as in seismic, there's always an automatic gain control that's put on. And this is kind of what you see here. So we've got a couple of reflections, right? Different amplitude, you apply an automatic gain, or you apply a gain factor to it to account mostly for the spherical spreading, but also perhaps for attenuation. And then you end up with something that looks like this. So when you see the final radar record, they should have on, just the same as on seismic section, all of the kind of processing details that went into that. So here's a typical radar ground. Got survey location here and time here. So that looks pretty familiar. Perhaps the only thing about the time axis is that this is in nanoseconds. So your orders of magnitude different from what you do in seismic, but everything else is kind of the same. We've got some direct arrival that's happening right here, and then we've got these hyperbolas that are coming in that look like this. And a hyperbola will be understood with an example that looks like this. We're going to again set a shot off and measure at the location of the transmitter, kind of pull this whole thing along. So not the same as before. Now we hit, get reflection. So that would give us one trace. This one over here. If we move the whole thing over, we'd be closer to the apex here, so get this trace. And eventually, if we pull, and zero offset is exactly right, we're just pulling the transmitter receiver off like this, and we get this kind of a hyperbolic shape. And from that, we can actually get the velocity of the wave inside. If we have buried pipes, might come up some. Here's an image that comes up from that. So each of the buried pipes give rise to a hyperbola. And we also have some flat regions in here that are coming in. These tanks are actually sitting on a bed, so it's a flat bed, and you're sort of seeing those flat beds in here. And then there's another horizontal reflector that's coming in there. So GPR systems come in on just a wide variety of flavors. Here's a guy doing archaeology. He's pulling the system along. Sometimes they're actually in two antennas that you can move. So you can have one. This is a transmitting antenna. So it's basically just a wire. I mean, it's a generator hooked up to sort of a T wire. And you have one as a transmitter, the other as a receiver. You can walk along with them, you can put them apart, you can turn their different orientations to get different polarizations. You can collect data in a common midpoint gather. So if you take the transmitters, you just progressively move them apart, common midpoint, or you can do a common offset. Machines are often small enough that you can push or pull them. Here's engineer, utility engineer. He's actually using something to try to find buried wires or things in that. And he's got a grid, plastic grid here, and he's got his GPR unit. He's just progressively moving this over. And then he's got a screen that's showing him in real time what he's got. So when you talk about resolution, if you go to high frequencies, you actually can get very fine resolution in the order of centimeters. That's it. In British Columbia, we had a place, there was an aquifer that is being used, and wanted to see if we could detect that with GPR, because GPR is sensitive to water content and lithology. So that's one reason to try to use it. Data can be acquired with zero offset, and we also want to acquire DC resistivity, so that's what we did. So here's the cover here, and here's the system that was used, and we just kind of carry that over top. And there's a few things about this that I think are interesting. One is there's definitely a reflection in here, so we're seeing some horizontal lithology. And then at some point, we actually changed the character. We're seeing, sort of deeper over here. We've got maybe some layer that's kind of coming through here. Same type of analysis or a critical analysis thought process that you used to with seismic now plays a role here. One of the things perhaps that's notable is that we kind of lose information over here. If you're on the right-hand side, you get to see fairly late in time. If we're on this side, we see, we don't see it. So first question is, why might that be? Any thoughts about if you're going over something like this, why you simply don't see it as deep in one location as you do in another? So the question is, in looking at this, there's a radar ground. Over on this right-hand side, we actually see, it seems like we're seeing fairly deep down. We've got reflections of signal that's coming down at late times. But over here, it's just blanked out. We're just whited out.
Left hand side is more conductive.
Right. So when I mentioned earlier about the attenuation of the waves, if you're in conductive environments, the waves just attenuate out. And that's what's happening over here. We did a DC resistivity survey over here, and this is the resultant inversion that we obtained from that. You can see that over here, the red is indicates low resistivity material. Over here, we've got low resistivity material compared to here, and that kind of correlates what we have with radar. Locating underground storage tanks. We've got both buried tanks and the buried beds. This is what we see from that, and then you can take this and you can take the data and make it actually into a cube and then sort of slice it at different depth slices. You need to convert your time to depth just the same as you do in seismology, but they can find, like, okay, here's an average velocity that I'm going to use to convert time to depth, and when you do that, you get images at 3, at 4, and at 5.
So I have a question here. Previously, for all the other EM method, normally when you do the inversion into that forward modeling, is it the same here for the GPR inversion? Do you need to run forward modeling?
No, and here this is again just like seismic. You just look at the data.
So you just look at the radar ground
Mhm.
and then it's basically in time domain.
Mhm.
So you don't need to do any like Fourier transform or.
No, there's probably all kinds of processing steps that you could use, but as a first shot through, it's just a matter of basically looking at your data. And you've got particular features, like if you've got, a wire or a tank, as you go over it, you should expect some kind of a curve. If you've got some type of layered structure, you're going to see a coherent reflection horizontally with time. If you've got it dipping, then you're going to have to, you'll still have an apparent dip, and then you have to effectively migrate those data. So I think the first other processing step that's sometimes done at a more sophisticated level is to do a migration of these data, to at least try to put things back in their right geographical location.
So mathematically, what does migration do in data processing? Like, what does it work?
Oh, wow, you should be asking all your friends here. They're the expert in that.
Yeah, because I have, that's a kind of new terminology.
I think I might have one example, but basically, if you have a
simple for my
so let's suppose I have this, right, and I'm sitting here. The reflection I'm getting is actually from this way. But what I plot is this reflection that I'm getting in here, which seems to be at one particular time, actually comes from this point here. So I've got to somehow go from reflections. So I've got, here's my reflective surface, right? And I really know that this reflection could come from anywhere in some kind of arc around that, the same with this, same with that. And then I'll use that to actually show that from my radiogram here, that the true slope is actually goes one way or the other, but kind of would go like that. So you're basically trying to put the reflectors back kind of in their proper description. Yeah, there's migration is probably the single most used process in seismic data. And for most of the GPR work, however, it's not even carried through to that migration level. Most of it's done pretty simply. It's just like that engineer looking there, see where the targets are, and
to generate this radar, basically you need to have measurement at different locations, right?
Yeah.
So if you only do measurement at a single location, is it possible to kind of generate any useful information?
I have not seen a case where somebody has done a single GPR trace and then made an interpretation from that. Because really in looking at this, okay, so let's suppose I took so I suppose I'm going down at the center here, and right, so I've got something up top, that's probably bigger, right? So that's my trace. This a single seismic trace is got some squiggles on it. It's pretty hard to know which of these squiggles might be useful. But the moment that I start to collect these, then I find out, oh, there's coherent signal in locations. And if it stays flat, coherent signal stays flat, it's like, okay, that's probably a reflection from a layer. And if it's got some character to it like this, then, oh, that's probably a reflection from a hyperbole from a tank. So it has some meanings, but I can't imagine a circumstance where you get one record and then somehow that's going to tell you a lot of stuff.
So for my case, it's actually very, I would think basically the system that uses a GPR, but what they measure is actually at a fixed location. And then they generate thousands of traces. And then they compare the difference between those traces.
Well, if you were able to, I don't know, do something so that you put in like a very different pulse, a different wavelength or something, so that a particular pulse maybe has a higher frequency, so it decays out earlier than another pulse which goes in farther, then maybe there's something to be done there. Because that would then be similar to what we ordinarily do as a sounding. I mean, sometimes we do a DC sounding or an MT sounding, and we just sit at one point, right? But we're now looking in the earth, we're doing multiple frequencies, and we see deeper or shallower depending on, and then we can combine that information and get something useful. So that's right. But if you're putting down a single pulse, yeah, I don't see how you gain much information from that.
Can you talk a little bit more about their like first return and
the first arrival?
Oh, the first arrival.
Yeah, the stuff up in here.
Yeah.
Yeah, often that's pretty complicated. I just show you something, but there's a lot of stuff happening right at because you've got your antenna, you've got a radiation pattern for your transmitter, radiation pattern for your receiver. You've got short offset. There's a lot of stuff going on in those first few nanoseconds. Sometimes you just get all kinds of energy coming through, and it's just hard to know what it is. And we've talked to even experts, like Peter Anand, who developed ground penetrating radar systems. I've asked them, like, well, what do you do about, this really early time stuff? And he basically throws out his hands and says, well, we just had to ignore that and start at some early time, but later than right at zero.
So like for example, in this case, basically after, so if you don't have this kind of tanks, like the area between two tanks, you basically don't see, you don't really see any kind of like reflection. So, so in my case, basically, after a certain point, it's just like exactly the same as that. There is no really like kind of reflection you can see by plotting the radar ground. But they argue that probably their signal has amplitude smaller than the noise. So I just want to kind of verify with expert, is that a reasonable argument?
Well, it may be that their signal is smaller than the noise. But then there's a question, okay, so now is that the end of the story? If they're then trying to say that they can get a lot of information out of it, even though it's buried in the noise, have to look at that pretty seriously.
Yeah, so they said, yeah, from the time domain, when they compare the amplitude, basically, after a certain point, you just see noise. But they say they need to do the Fourier transform to change it to frequency domain, and then we can see the signal.
I mean, there might be something in that. I mean, you can imagine a case where you've got, some signal, and then you contaminate it with, let's say, 60 hertz noise. So that when you then go and look at what your total signal is, it basically looks like 60 hertz, you can't see it. But if you did a Fourier transform, that 60 hertz, you might be able to take that 60 hertz noise out, and then you're left with something. So,
But I think when I look at even after Fourier transform, there's no like, basically the background noise is not like a single source, like you need one frequency. It's probably like white noise.
yeah, so here's where now it's very difficult to make much progress in saying that, yeah, it's good or not. And here you really need to be able to step through exactly what's happening, what they're doing in the processing, and also to simulate. You need to be able to simulate the data that you would be expecting to see.
So similar to forward
Do forward modeling, right? Yeah. Because it's interesting that there have been people that have tried to do, the inverse problem somehow, right? And then you ask, well, how do you do forward modeling? You say, well, we're not really sure. In fact, we're not even sure about physics. Well, you can't do that.
That is exactly the case. Yeah.
So maybe that's a question that could be posed to them, right? So it doesn't necessarily get through what they're doing and all of their processing and that, which might be proprietary, but you should be able to come up with an Earth structure and do whatever, a temperature, put your temperature profile in, put whatever else you want, and say, okay, here's my Earth, okay? Here's all the physical properties. Forward model the response that you see, perfect diagnostic. If they cannot do that, then they're somehow doing stuff without even understanding the physics of the problem, and that would put up all kinds of warning flags.
So for forward modeling, basically you need to know their input signal, right? Like what's their transmitted signal, what frequency, and what's their wavelength, like the extent, right? So yeah, because currently that's a black box to us.
No, but maybe exactly what they do, I mean, maybe it doesn't matter. If you just say, okay, I'm going to put in some kind of a pulse, right? And so typical pulses might be something that looks like that. So that's going down now into the Earth, and your Earth is characterized in your case by temperature as a function of depth, and presumably sigma is a function of depth, epsilon as a function of depth, and I'm not sure how T enters in, but they've got some physical system whereby they need to be able to convert this to what you get in a radargram, right? Because that's what they're doing. They're starting with this radargram, they're going back and telling you that. Okay, so now you can say, look, let's talk about a simpler problem here. Just so that I understand. Okay, here's my Earth. Now you put up your radar system, and it can be even a straightforward radar system, right? And just to show me what I'm going to get out as far as a radargram, and then let's see what we get. At least that's the forward problem. Actually, having kind of got onto that trajectory, I think that would be a really, really good way of at least finding out if there's you'd find out what the physics is, and you'd find out if they're just smoking, right?
I think we cannot do that because based on my interaction with them, we have the understanding of why, let's say, temperature kind of cause their any kind of anomalies in their signal. I don't think we can do that.
But this is then this is a lower level question to ask, because they might say, wow, sorry, in our final processing, we have a lot of things, we're not going to tell you exactly what's happening. And so now we can keep that underfoot. But if you go this other way and say, look, I just need to understand, here's the Earth, this is what you claim you can get out for me. I just want you to do a forward modeling. I just want to see what that radiogram looks like. I would do that. Okay. Here's a case system. So here's your system. It's 100 megahertz system, and you've got GPS on here, and then there's also a tracker to see how far you're going. And you come out and you get a radiogram that actually looks something like this. So you can see there's reflection in here that indicates the bottom of the tunnel. And then utility mapping. This is again smaller. These were 2 pipes. So there was an iron cased water pipe and a PVC gas pipe. GPR is an electromagnetic signal that's going down, right? And it's sensitive to changes in electrical permittivity, so dielectric constant, but it's also very much sensitive to the electrical conductivity. So if I have a wire there, I can still get a strong reflection, GPR reflection, from a wire, as well as if I just had a PVC pipe that has no conductivity, but it's carrying water. The water will get something. So 2 reasons that you could be sensitive to. And you go on, do the grid, get your sort of 3D radar section, and then at one particular depth, here you see the gas main, so that's a PVC pipe, and then here at a greater depth and moving over, here's the water pipe. You don't need to do any sophisticated processing at this level. You're just trying to detect something that you think is useful, pipes, cables, whatever. Because it's very sensitive to water, one of the places that GPR has been used is in mines. So in that case, here, this was actually a mine in Saskatchewan. It's a potash mine, and water was struck and it was just blasting in. So you don't want to have that happen. One way of trying to see how you're doing is to have a GPR system. And in this case, it's easy to think about a GPR system on the floor of your drawings. And you're looking down, but you're really concerned about water coming up, right? So you have the GPR system up on top, and that's what they're doing here. So they're going along, and they put the GPR system here, and then they're trying to see what's there. You can do GPR on the ground. You can also do it in the air. There's one aspect of this, of the following case history. It's about trying to find the depth of a glacier that I think it's interesting, and it carries over also perhaps to seismology and seismic processing. So I'm just going to flip through this kind of quickly. But anyway, there's an area in Switzerland It's been monitored for a number of years. It's sort of an ice rock glacier, so there's a combination of cobbles and rocks and ice, but it can be dynamically unstable. It can just start sliding down, and that can cause problems. So you want to monitor not only this particular one, but also use it as kind of as a bit of a laboratory to try to figure out, try to understand these rock glaciers. So the first thing is the physical properties. We've got a number of different materials, unconsolidated sediments, ice, partial melt, compact debris, and the velocities that you have. So dielectric constant velocity related vary between something that's greater than 140 for the ice and unconsolidated sediments to maybe 80 for the saturated sediments. So there's not a deep dynamic range, more of a factor of 2, so this is probably getting a bit closer to things that you can see inside of them. There's been a couple of boreholes that have been drilled, and this is sort of an interpretation of what the velocity is as cross-section through the hole. They initially thought we should, if we're going to get good resolution, we should be right close to the target. So we've been talking about that throughout the course, right? You want a better resolution, you're going to be better off being as close as possible to the target. So they did ground GPR. Turned out that ground GPR didn't work that well for them. We'll talk a bit about that in a second. And then they also did heli GPR. So now they're mounting the radar systems on the underside of this helicopter, and then they're flying over the region. Maybe this looks somewhat familiar to you. So this is the ground GPR, and here was the raw data, the filter data, and the final process data. That's pretty mucky. There's really not. It's pretty hard to see very much in that. When they did the heli GPR, however, these were the raw data. Here was the filter, and here's the final process data. So you can start to see there's something happening in here, and there's a reflection that comes in. So this is not nearly the kind of clarity and caliber that you see in seismic work for oil companies usually, but actually for large-scale tectonic types of things, sometimes they're not so much better than this, and just being able to kind of see concentrated bands of reflections, giving some information.
So the filter, what do they normally do for the filter? Like,
Oh, I have no idea.
oh.
Yeah. But they just put this forward like, okay, here's our filter data. So they've got a number of processing steps. I don't know what they are. So their interpretation here was that there's sort of a major shear zone between ice-rich and ice-poor that's kind of coming along here, and then there's fault boundaries that come in here. Those are particularly important because that's the region along which things would slip. So that was along one profile, and then you have a different profile along H5, but you're able to get some general structural information from what's going on with the helicopter GPR. What this did, it actually provided for them a new way of thinking about this. So they kind of reformulated how they thought about these rock layers. They kind of be something similar to naps, where you've got thin regions of decalment. It kind of gives them a different way of thinking about how these glaciers are formed and how they might move. But the the thing that was, I think, interesting about this is that you ordinarily tend to think if you take your transmitter and receiver and you put it up really close to something, that you're going to get best resolution. But when you do that, in this case, there's just so much cobblestones and structure, and you get things that are bouncing off, and you just get a mishmash. So sometimes it's actually easier to get more information by stepping back, and then you effectively have poor resolution, but at least you see something. So the context is the context is something like this. You can imagine a whole bunch of little scatterers here, right? And then you've got maybe bigger units or something kind of coming down here. And you're actually really interested in kind of seeing this boundary. But if you're sitting right up here as your transmitter and receiver, then you're so close to all this other stuff that's coming back, and your radargram, is just kind of like that. If, however, you put everything up in the air, so now you put up in the air, then you don't have the resolving power to see this. You're farther away from these small scatterers, and you're more sensitive just to being able to see what this unique for. So, yeah, sometimes being too close is not desirable. I think we see that in our regular lives and certain things too. Here, I remember Lindsay and I were in which museum was this?
It was Mexico City.
Mexico City. We're up in the art gallery, and there's this massive painting on the wall. And we're walking right by it, and you're looking at this painting, and it's like it was kind of overwhelming. I mean, there was just so much happening, and you're having to kind of look around, and we couldn't figure out what it was. I mean, it looked impressive. We couldn't figure out what it was. So we walked around the chamber, and then we were on the other side. Okay, and now you're looking at this painting from afar, and it was amazing. I mean, it's suddenly, the picture comes out, and you're just like, oh, yeah, that's great. So you have poor resolution, but perhaps greater clarity of information. So here's an application that might be of interest. It's hard to know where this is going to go, but people are always thinking about driverless cars and what the sensors are that are going to be on them. I think we're doing a little bit better these days than when this picture was taken. But these are all sensors that are trying to gather information. There's GPS, there's LiDAR, there's cameras. These things work really well in good weather, but in bad weather, rain, snow, sleet, fog, they don't work so well. If you come along and change road signs, or new tree grows up, or a tree gets cut down, or road stripes are added, that can confuse these sensors, and that could not be good. So I think we're always in a situation where we kind of need additional sensor data. So the question is, what could you do? Here was the idea. It comes out of MIT Lincoln Labs, and they've designed a system. It's a GPR unit. Actually, it's a collection of 12 of these guys that goes underneath the vehicle. And the process is to, first of all, take that system and run it over the roads. So you go up, you collect GPR data. So now you manage, like, okay, this, and I'm just going along the road and seeing what I see. And then you store that. That's your reference data set. A little bit later, come over different conditions, and yeah, you want to find out where you are. So you want to do another radar experiment. So now I'm going to do radar here. I'm driving along. Here's my radargram, and then I want to say, okay, well, what's the match of this radargram with the one I had previously, and then that helps you locate it. In order to do that, they do kind of particle swarm inversions and try to find that place on your map that you've stored that matches best with the map that you just have. So you want to cross-correlate that basically in real time. And the movie that I'm going to show you, this guy is doing it there. They collect the radiogram on clear days, and then there's snow on the ground. And then he's going 60 miles an hour and trying to get 4 centimeter inline accuracy on that. So it's certainly something at a slightly new level. Maybe we should turn the light on.
MIT Lincoln clear day, MIT Lincoln Laboratory demonstrated real-time localization of a vehicle at highway speeds during a nighttime snowstorm. Side-by-side measurements from the nighttime snowstorm tracking localized.
Is it a GPR as well?
I think that's, I mean, the SAR, or SAR.
I don't know, it's a kind of radar that's covered water, on Mars subsurface, ice.
Yeah, I think that's either SAR or INSAR or Landsat.
It's a radar.
Yeah, I think that's probably a Landsat.
Um satélite. Satélite.
Yeah, I think that's the word now, by
Um
JPL.
satélite. Do espaço. From space.
So basically they have, it's like GPR, but it's kind of mounted on their satellite. So they kind of, I think the project is called Marsus. So they kind of get to, because Marsus, they have this very thick ice. So they get penetration very deep, like about 7 kilometers where they see the reflection. Yeah, I have seen that paper. Yeah, it's definitely based on GPR. Yeah, they also send out this project. I think they work very similarly.
Yes.
But yeah,
ICE has a dielectric constant that's really low. And one of the first real uses of GPR from a geophysics standpoint has been to fly a radar system over various ice fields. And then you can use that to map the thickness of the glacier.
Now, about this methodology of MIT, works only for concrete roads, isn't it? Not for round roads, this technology.
I don't see why it wouldn't.
Although, like, the gravel road, to that point, could be sort of a similar scenario to what we showed with the rock glaciers. If you are too close to a bunch of gravelly,
Maybe.
I don't know.
If you're losing like a lot of energy there somehow, then that would be really hard, but if that's not the case.
A clay road would be a problem,
Yes.
Yeah, if that's not,
It
like,
works only in the city.
probably.
I
A clay road would be a problem.
Pardon me?
A clay road would be a problem, like.
I think I don't see any problem for gravel. Okay. A rock glacier is a bit different, like you got like a chunk of rocks in there. the mixture of ice and they got different dielectric constant that generates signal. It's like it makes a lot of scattering. So you got a lot of junk under the surface, which actually hides all the signals from the deeper part. So but for the gravel, I think it's pretty fun.
Well, also, just, I mean, you may not have to see like perfect reflections or anything like that. You're just seeing a signal. That signal could look, kind of chaotic, and as long as you can match it, then
It compares the signal you are registering in real time with a pre-existing one.
correct. That's it. So whatever that signal is, it's not like you having to.
Refractions,
Whatever, as long as it's the same, it's not a
As long as
random
it's the same
noise
signal,
change
right?
with time.
Na estrada de chão, como é que faz?
Aí se é qualquer pedrinha metálica que for enterrada 10 metros, 30 metros, que for que deu um sinal, isso se repita.
Beleza. Mas e um sinal pré-existente, veio da onde?
Aí tem que ter passado por lá antes.
Isso.
You need to previously
Mhm.
go in this way, whatever it's the kind of, and then to.
Like a
Yeah.
Google Street View.
Yeah. That's
Well,
Google Radar View.
I mean, it takes things to another leap, but I mean, if this technology actually proved worthwhile, then you can imagine all cars being
Yes.
equipped with this and talking to each other and upgrade, upgrading
Improve
what
their
the
map
profile
themselves.
of the subsurface is. You know why I'm enthusiastic about this for a couple of reasons. One is, I mean, it might have some potential, but the other thing that I think is really great about this is that it presents in a way to the general public the use of geophysics and the idea of making use of something inside the earth, seeing inside the earth and getting something useful out of it. And really, if that connects with people, then they've got a whole bunch of concepts that are really useful. Like, oh, I could have an instrument, I could put some energy down, I could get something back, and I can actually make use of that. And the fact that you've got, maybe a different instrument for a different kind of thing. Like, that's not so foreign. Like, I've already got the idea that this is kind of how geophysics works. So it's kind of like one of those little conduits that if you open up, might actually have an impact far beyond what you initially thought.
Does it make any sense to think of a GPR offshore? Possible to?
Well,
detect
it's the
and-
conductivity of seawater that really gets it. It only
Yeah, that's the
propagates
point.
10 centimeters. Yeah. So, yeah, you need to have that resistance.
Você vai comigo lá na farofinha, assadinha meio. É engraçado, cara. Vai um dia, voltou um dia, e você volta na farofinha ali, agora ela fica.
That's true. That's true.
I'd like now to start the last part. So we've done everything from the point of view of grounded systems or control source systems, DC, and then all this time domain, frequency domain in the quasi-static, and now the GPR in the really high frequency. So that kind of spans all of Maxwell's equations from 0 to really high. So that's great. We also looked at natural sources of just a different kind of configuration. What I want to do now is turn our attention to the fact that the electrical conductivity, and in fact, any of these different physical properties. So suppose that I've got a rock here, and I've talked about it having some particular conductivity, and that's just like a single number. But if I'm going to put so here's some voltage, I get some current that's going through here, and I get, a V is equal to IR. If I convert this system, if I put a particular current through here, and if I have an oscillator that's got a high frequency compared to one that's got a low frequency, I'm actually going to find that the electrical conductivity that I get out of here, the resistance that I measure, actually depends upon the frequency. So that's not something that we've looked at this point. We've thought about, each of these physical properties. Like if I've got a rock, it's just got one electrical conductivity or one magnetic permeability. That's not really true. This conductivity actually depends upon the frequency at which you're doing the experiment. And now that opens up a whole host of possibilities for how we might capitalize on that. So that's what I want to do. I'm going to talk mostly about the dispersive properties of electrical conductivity and show where they're useful in induced polarization. So where does that come to play? We're going to refer to this frequency dependence as saying, well, the electrical resistivity is actually, or the conductivity, is actually a complex quantity. It has a real part and an imaginary part. The uses of this are in minerals industry. That's one of the really big ones. Permafrost studies, some aspects of groundwater, seafloor massive sulfides, again, kind of minerals application. And there's a lot in geotechnical, in fact, hydrocarbons have kind of an IP signature. And so there's connections in a lot of places. And I want to take you through just to talk about the conceptual model of IP. But how many people here have been involved with an IP experiment or have any idea what it is? Anybody?
When I was at the college. In the 90s.
In the 90s.
I worked, it's a kind of gold prospect.
Oh, yeah.
That was detected with IP.
We'll have to get you to give us that case history.
Yes.
Anyway, we're going to talk about the IP experiment and how it's related to the DC resistivity and look at some examples. So induced polarization, we measure, it's something that we can measure macroscopically, but it is a microscopic phenomenon. And what we've been talking about so far, when we did the DC resistivity, we'd have no current in the transmitter, and we turn the current on. Right? The moment that we turn the current on, we measure a voltage. When we turn that current off, we lose that voltage. And so if we looked at the source current and we looked at the measured potential, they would have the same waveforms. One would be different amplitude than the other, but that's the information that we have. If the material is chargeable, then when I do the same experiment, turn the current on, then there is an initial rise in the voltage, but then it actually keeps going. It doesn't stop, it just kind of keeps going. And then when I turn it off, it decreases immediately, but not all the way to zero, and then it just slowly decays away. So it's kind of like the Earth doing something, it's basically acting like a capacitor, and is kind of charging up while we have the current on and discharging when we take it off. So here's a phenomenological idea. There's actually many physical ways in which you can generate something that has particular chargeability or complex conductivity. But this is one of the nicest ones, and it's fairly rooted in physical reality, and it's a great way to kind of think about things. Sometimes if you just have a cartoon image about how things were, and it's like, oh, I kind of get it. So here we are. So let's suppose that we have at a grain cell level. So now we're looking at small scale structure. There's a couple of grains in here, and maybe this is a pore throat. The surfaces of the material, maybe these are clays, and clays generally have a net negative charge that's associated with it. And so if the fluid is electrically neutral, there's a number of positive ions that are going to be drawn to that. And then in the fluid, there's going to be positive and negative ions. And so you can kind of think about at a steady state, everything is sort of electrically. So now we're going to take this, we're going to apply an electric field to this. And we know what happened if we So suppose I had something like this. I got positive, negative, positive, negative. So now let's go, I apply an electric field to this. Then what would I expect to have happen? How are these charges going to move?
The negative charge left positive balance.
The negative in the left hand.
Yeah. So we can think about building an electric field here as having a big plus charge here and a big minus charge here, right? So in that case, the plus charges are going to want to go this way, and the negative charges are going to want to go this way. And the thing that can happen is that these ions just kind of get clogged up at this pore throat, and also we get sort of a redistribution of currents here, or charges there. And the result of that is shown up here. So we apply this electric field, so that's going to kind of push the positive charges this way, pull the negative charges that way. And then if we look at the system and we say, okay, where's the charges? We see, well, basically we've got a kind of an electric dipole. Overall, it's still electrically neutral at a large scale, but we've got a small electric dipole here. Right, so that's going to give rise to a voltage that we could measure away from that. Okay, Roberta, you look really puzzled.
Yeah, because should it be in the opposite sense? If I look at the battery,
Yes,
if I look positive, the electric field it generates.
Yeah, so the positive electrode of a battery. So if I hook this up, that's like putting a great big positive charge here, right? So I put a positive. If I have if I have a charge, it's going to try to get away from the positive charge and go to the negative. So it's just like
The electric field there is exactly as you put it here, right?
yeah, the electric field.
So the negative charge will move left.
Yes, so the negative charge is trying to move this way. Positive charge is moving this way.
So the induced charge is a negative in the left and a positive in the right. The negative will move left.
Because of the throws, you have
Yeah.
These just get
Clogging.
clogged up, so we ended up with more.
Okay. So they just can't go through this.
Yeah, they kind of get blocked up. At this
Yeah, I
point.
was thinking that. Okay. I was thinking that, okay, as long as I have this external force, some of the charge will be able to cross this throat.
Mhm.
And then even if you take out the external force, they wouldn't be able to reproduce the initial equilibrium condition. So
Okay, so
I was
that's
thinking a different situation.
no, but it's so close to this, right? The only thing that's different is just think about like, okay, I'm trying to put positive charges in here, okay? And then let's just suppose they get blocked up. That's the easiest way to think about it. So now those are going to get blocked up. If I have another, so eventually I get a lot of positive charges here and a lot of negative charges here, and they like to kind of get through to each other, but they can't. They just get blocked up. And then what happens here if I have another positive charge, right? So, in a way he wants to, so here's my battery, so here's my big positive. So he wants to go this way, but now there's this excess of positive charges here, so there's a repulsive force this way, and so it's kind of going to get equilibrium. So that's an important part of this thing. Also, initially when it starts, you can probably get quite a few charges in here. A little bit later, it gets a bit more difficult because they're starting to be repulsive. And at some point, you'd expect, okay, equilibrium. Like I've got a positive charge here. He's driven away from this one, but he's also driven away from this. Equilibrium. So this kind of a cartoon turns out to be absolutely invaluable in kind of thinking about, understanding this process. That I start with some kind of neutral situation, I apply a field, I'm going to get charge build up. So that's kind of like a capacitor, right? And then if I take that electric field off, things are going to go decay back. So what materials are chargeable? A lot of minerals are, like pyrite. Okay, so here's where Sergio is going to come in. Chalcocite, copper. So all the sulfides are hugely charged. This is why they're so valuable for mineral exploration. And then other rocks are too. You got shales, and schists, and gravels. So let's return to that
They
thought
found the
process.
pyrite instead of gold.
What was this?
Professor said that the Marcus found pyrite instead of gold.
Oh.
In
So
the-
English they can make
Like this, right?
They call like fool's gold as well.
Fool's gold, yeah. But it's still pretty.
It's a vector to find gold.
So now we can understand a little bit more what the signal might be. Okay, we take this current, we turn it on, and so think about what happens here. So we've got, let's suppose, some potential electrode here. We turn the current on, right? And then we get all this charge built up. And if we look at the potential that we measured, the moment that we turn the current on, we get this increase. And then while this current is on, while this current is on, these charges are continuing to build up, so the voltage is actually going to increase. The moment I turn this current off, the voltage decreases, but there's still these charges there. So then they are going to decay away. So the procedure is, and this is what we would expect to measure, is that turn it on, got this increase, the charges gradually build up over time, and then they asymptote. They're going to reach some steady state. Turn the current off, this drops down, and then the charges are going to decay. So this is a voltage, when I measure this after the turn on, this is a voltage that is related to charge buildup. So that actually might be something that's useful to measure. It's called the secondary voltage. In 1959, a guy named Harry Siegel looked carefully at this, and he recognized that the effective conductivity of something that was chargeable is given by this. So the effective conductivity of something is chargeable, and the quantity that was introduced is called chargeability. It varies between 0 and 1. Chargeability effectively reduces the conductivity. The theoretical value of chargeability could be seen in this slide here. It's the relationship of phi s right at the time of turn-off. So this is the secondary field that is obtained by all the charges that are accumulated, divided by what's called this primary field phi eta. So that's this guy here. So we measure this difference, phi s, over phi eta, and that is our measurement of chargeability. So it's always going to be less than 1. So in the time domain, actually anything that we measured from this kind of decay is like, okay, that's related to this chargeability. And so I could do all kinds of things. I could just take a value at a point, or I could take a time channel and measure the area under here. There's different ways that I could just sort of capture the idea that there's some kind of decaying voltage there. And similarly, in the frequency domain, you will also have the same kind of effects. Imagine that if you had a high frequency source that went like this, so it's here's the value, it's sort of high frequency. When you thought about the charges being built up, they don't really have time to reach their asymptotic value, so they charge up and then, oh, current's on the other direction, now and charge up in the other way. So you get something that looks like that. So you'd have a peak-to-peak voltage that's V1. On the other hand, if you had a low frequency, then it has more time to charge up, and you're going to have a peak-to-peak voltage V2, and that ratio of those two things is an aspect of chargeability. Or the other thing, and here we come back to this, amplitude and phase business. If we had a source function that looked like this, if the electrical conductivity is complex, then we are going to measure a phase shift between the source current and the receiving voltage. So if we can measure that phase shift, and usually that's just in terms of milliradians, then that's a valid number. How do we then do this forward modeling, and how do we understand the process mathematically? Well, chargeability is generally a small number between 0 and 0.2 or something like that. So that means that we could think about the IP data as being resulting from a perturbation in the electrical conductivity. And we can do that. In the end, we can write the IP data as some sensitivity times eta, which is the chargeability.
So that's our final representation. So this is a linear problem. So it's just like that linear inverse problem that we were dealing with the other day. And J is a sensitivity matrix that is already obtained because you're solving the DC resistivity problem. So the idea is it's kind of two effect. When you sort of do the DC IP experiment in the DC, you take the maximum voltages, you invert that to get conductivity, and then you use the perturbation technique to find the relationship between the IP data and the chargeability. So just a summary of the data types. Anything that's connected with this in the time domain, a value, integrated value, that means it could have different dimensions. One could be milliseconds or it could be dimensionless. And the frequency domain, a phase would. So let's just go back now to the problem that we initially worked with, which was the DC resistivity, but now we're going to change things. We use the same kind of models, but we're going to change things so that I've got a uniform conductivity, but I'm just making things chargeable. So this is a chargeable block here, and now if I go ahead and I do my DC resistivity experiment, but look at the chargeabilities, I get a pseudosection that looks like this. So I can plot. Not sure whether. So let's do this. So here's our A, B, and here's our M, right? So we're going to, let's first of all think about doing the DC resistivity experiment. And so now we put on, here's our current. We're going to turn it on, and then we're going to eventually turn it off. So this is I of t, and my voltage, V of t, the moment that I turn it on, it goes up to some value, and then it increases because of the charge, and then we'll get there. So at this point here, let's suppose I'm sitting right here just prior to turn on. I've got this particular voltage. So I measure that particular voltage and I convert that to apparent resistivities. So my apparent resistivity is whatever that voltage is, V divided by G I 2 pi. So this is what I did in the DC resistivity. I took this value here, converted it to apparent resistivity, and then I plotted it there, and then we moved everything over, and then so I get my pseudosection, right? What I'm now going to do is exactly the same thing, except that when I turn this thing off, it drops down like this, and then it kind of comes out like that. So I'm going to pick a time, let's suppose out here, it's got here, and I'm going to measure, let's say, some secondary field, and that's going to be connected with the connected with that charge. I'm going to do exactly the same thing. I'm going to plot something in exactly the same pseudosection, except that here the number that I'm going to plot is not going to be ohm meters. It's going to be whatever the value of this number is, or and whatever units it is. So maybe in this particular case, the unit that I'm measuring is in milliseconds. Then this number here is going to be also in, now this will be milliseconds. Okay. So I'm going to get exactly the same kind of pseudosection plot. The only thing is that the numbers that are being the numbers that are being plotted here
are now milliseconds, so these are no longer apparent. Okay, is that copacetic? So that's what happens here. If I corrupt this now with chargeable blocks, so let's suppose these are clays or graphites or something like that, then I get this same screwy pseudosection. Can't make any sense out of that. And also the same thing happens with that GIF model. If I have these two chargeable bodies now in this, I get a final chargeability section that looks like this. And if I drill that chargeability high, again, I miss it. So exactly the same things that we had in the DC resistivity, but now we're talking a different quantity here. So now we have to, we're going to invert the data. So how are we going to do that? So first of all, we're going to collect this DC and IP data together, right? So we're going to collect these numbers, let's get rid of DC, and then we'll collect something that's associated with this decay curve. That's our IP data. Collect those together. We'll first take the DC data, and now we're going to invert those to get our conductivity. So that's the first thing. Remember I said that there was a sensitivity matrix that allowed us to kind of relate the chargeability data to this conductivity model. So we use this conductivity model, calculate sensitivities, and that's going to give us now the mapping, the sensitivity for IP data. And now we're going to take that IP data and invert that to get chargeability. Okay, so it's a two-step process. First step involves getting that conductivity, and the second step involves the idea that the IP data are just a perturbation of that conductivity, and so we're going to now invert for that kind of perturbation. So if we look at those examples that I just showed you for a buried prism, here was the chargeability model, here was the pseudosection, and now we do the 2D inversion, and we got something else that looks like that. So that's pretty nice, right? We've got a body that's in the right location, and it's nice and chargeable. That's great, and predicted data looks like that. This one's even more dramatic, where we've got all this little junk up here, and we invert that, and we find our chargeable body, but we also find these little chargeable pieces of junk that's sitting up at the surface. And then here was the GIF model. So we have this confused pseudosection, and we end up with an inversion that looks like that. So really pretty much paralleling what we had for DC resistivity, but we can now do it for this extra thing called chargeability. So let's now go through the case history. So now we're coming back to the very first case history that we did before. So I'll remind you what we had. So here was the setup. We're in Australia, and our question now is whether or not we can find a conductive and chargeable unit that is buried in this siltstone, and can we use that same DCIP experiment to do that? So here was the geology, if you remember. There was some volcanics in here. There was this black shale unit that was really highly conductive, and we're looking for a mineralized body. So now our physical properties are the following. So here was our rock units, and here was the conductivity. And we found that the thing that we were looking for, this Mount Nova horizon, had a high conductivity. Unfortunately, not the highest. The highest was the breakaway shale, but it had a higher conductivity than the other rock units. But now look at the chargeability. The only unit in that region that is chargeable is this Mount Nova horizon. So that is now something to focus on. We're going to go in and see if we can find something that is chargeable. To recap from the
the DC resistivity synthesis, we did the DC survey. Remember, we did a whole bunch of pole, dipole, and then we did dipole, pole. Inverted that, and we found this great big conductor on the right-hand side. That was the that black shale unit. There was a bit of a moderate conductor sitting here at E. If we look at the IP data, here's the pseudosections. Maybe one of the things that you might ask, when we did the pseudosections for the DC resistivity, they were kind of looking like this. So this would have been, here's our first current, and then here's all the potentials that we got. So this current to here gave us this apparent resistivity down here. These guys are all cut off. That doesn't exist, they just get cut off here. And the reason for that is that this IP signal is already small, right? So here's the primary, okay, that's fine. But now when we talk about these guys, they're already small. And if we talk about having really large offsets, you can't do it. Everything's in the market. So the pseudosections that we're working with are truncated like that, but we've got a pole, dipole, and a dipole pole of these. So again, we've got 20 pictures. We want to convert them to a chargeability model. So now it's going to be, now we do the same thing. So we're going to take this volume and we're going to find the chargeability. So the procedure was, first of all, we do the DC resistivity experiment. We invert that, we get that 3D conductivity model. Now we evaluate the sensitivities for that. And now we've got the mapping for the chargeability. We're going to invert those, so it's going to be the same cube. And then we're going to look at that through many different processes. Oh, it's over here. So we're going to slice it through the same way as we had done before. Back to front, front. And then we're going to do plans. So you can see that there's a lot of chargeability stuff that's going on there. So the red parts are highly chargeable. And now we're turning around and we're progressively just looking at the highest level of the isosurfaces. And you see that there's a region out here now that is really quite chargeable. So we put all that together. Here's kind of what we had. From the DC resistivity, we had something that looked like this. From the chargeability, we've got major chargeabilities now along this line here. This region in here was kind of moderate conductivity and high chargeability. So we identify this as being a potential mineralized zone. And this, in fact, is that Mount Nova horizon. This was the breakaway shale. That is the black line on here. Interestingly, there is some chargeable material sitting out here. And I mentioned this the other day that when we went down to Adelaide, we were showing him this and we were talking about this. And he said, oh yeah, you know, they had recognized that there is some chargeable material there that's not associated with the black shale. And they're thinking about going back and checking it out and seeing if that is useful. So in synthesis then, what has been really useful is this DCIP experiment. Getting that conductivity has been important,
but the information about mineralization has lied in the IP part, or the complex portion.
For most mineral deposits, the important effect is the grain polarization, isn't it? It's the grain polarization. What about membrane polarization? What's the difference of another model?
Membrane polarization models are very applicable for environmental studies and groundwater studies. For the mineral deposits, there's still membrane polarization, but then a metallic polarization where you've got a metallic particle, you're trying to drive a current through, and you actually get two sets of dipole charges, one on one side. I think that's probably a good place. Let's have a coffee break, and then we can see whether we want, how much more stuff we want to talk about on this, or maybe just start to find out more about what we're doing.
So the instruments of GC and IP application is the same instrument, and it's common to variable data.
Right, because like you're just changing the waveform, so on and off. Sometimes like people just process it together. So yeah, it's like you're planning to see. Just as I think at the this is more robust. You don't need to spend that much. But for IP, like especially we're seeing then you may spend a lot. And also, I think Doug will mention is that your equipment says there's no distinction between CCM and DC. Right? That's basically the same equipment, so they'll generate a lot of information as well. So then, okay, how do you?
But for mineralization, on one can perform only IP acquisition, not the DC.
They always do a DC and IP together.
Yeah.
So, but like sometimes they just use that. But to get the IP data, you need to first have a DC to chart it. And then if you actually even you look at the definition of IP data, it's normalized by DC.
Okay.
So that's already not the DC data, right? If this is a DC data, that's actually really. They usually spend a couple times, a couple wait time channels in the uptime, and they send that as DC data, and then they use that to divide the off time to get the
Okay.
Sure.
Natural light is.
Oh yeah, natural light.
O Sérgio é um cara mandou ali na cara dura agora.
Eu vi assim, um de vocês dois, você tá olhando pela visão periférica, mas nessa hora tentando minha vista aí pra não dormir, cara. Aí um de vocês estava se abaixado quando eu fiz. E daqui a pouco eu quase rindo porque o mais, cara, ele segura o riso, mas fica tremendo aqui a mesa, fica aqui assim. Falei, caraca, você não para de tremer essa mesa, pô.
Pô, o cara fez o microfone, velho.
Caraca, não, Pedro, vergonha já, cara.
Não,
Todo mundo é da casa já, né? Todo mundo de casa já. Tinha sobrando aqui.
O patrão tá aqui, ó.
Oi?
Outro aqui que tá carregado o laptop.
Vou botar no USB do meu laptop aqui.
Desse aqui.
Não, tem lá embaixo, eu pego ali. Aqui.
Sim, da voz. Que tá o laptop.
Ah, tá bom. Só botar a carga ali. Acho que eu esqueci de carregar. Ah, que hoje. Tô falando, tem um adaptador aqui.
Foi só CD. Só CD. Mas isso aí que a galera construiu era só CD?
Rapaz, cara, aquela garçonete tava muito sorridente naquela laço de baixo.
Exato.
Meu Deus do céu.
Não, cadê? Ah, tá.
Calma aqui, né?
Vou até tirar.
Acho que tem uma ali, né?
Eu sei que os vaidades foram para ele. Né?
Mata ninguém, então, a gente ficou. Ela falou assim, coisa assim, quando eu fui sair para uma aula no parque dele, onde você vai? Pode ir. Foi um calor de dia.
Imagina que demorou muito não. Ela foi com o cara depois.
Não, então.
Nenhuma saída pro boteco vai ser a mesma.
Você
Vai.
chega.
Você nunca mais vai dar uma saidinha pro boteco da mesma forma.
Bora pro emprego.
O Matheus estava sem filtro total.
Baixou a função.
O pessoal baixou, trocou o corpo.
Espírito maligno.
Aqui, os caras fizeram muito difícil uma vez. Aquele cara que era do. Tô na bocha de pilha, que era, sei lá. Rafael William. É. Assim, qual é o seu doidão preferido? Aí tava falando sobre o seu
Did you pull the EM examples too?
Caralho, tô puxando muito duro.
O pessoal do Pânico fazia o Rafael Pilha.
Rafael Pilha. Esse bicho tá vivo ainda, cara?
We added the
Deixa ele vivo.
attenuation.
Oh, é. O cara não se drogava de todo mundo. Fita de cassete, as porra toda. Pouco metal pesado naquilo, né? Isso é louco.
Quando ele aparecia, né? Rafael William super as drogas, não sei o quê. Você estava preso.
Yeah, so the value will show up here.
So at point, so at 10 to the minus, so like 20 ohmmeters or something. So at all frequencies, so that the velocity so let's see, so here we're this should be the velocity of light divided by 3, right? Yeah, 3 times 10 to the 8, that's correct. Okay, and then now if we look here at 10 to the something here, then our skin depth is sort of 5 meters, right? And if we look,
Yeah, so I think you could just read that value.
7, right? And then so at yeah, 10. Oh. 0.8 meters. Good, that's perfect. So there's another app. We used it for the GPG. This is, Lindsay had mentioned this yesterday. So it's geophysics for practicing geoscientists. That's the course that we use for like geologists or engineers or something like that. They're just like, okay, here's your introductory to geophysics, and we try to look at the various kinds of geophysical surveys, just a like quick brief overview of the introduction, and then just get them familiar with words and where it might be useful enough. But we do a GPR section in that, and there is one app that has been put together. And the main thing about this is that it connects the electrical permittivity or dielectric constant, the electrical conductivity, and the frequency together, so that you can get a sense of, if you put a particular frequency wave in, how fast is it going to attenuate, what's the skin depth, and then also what is its velocity. So that's just kind of an interesting thing, and I think, Tintin, from your perspective especially, just to kind of ground you, just go back to this and say, oh, okay, if I had this particular frequency, how far in could I see if I've got this conductivity? With the ADROC stuff, do they talk about what sort of frequency band they are working on?
From 1 to 100 megahertz.
So 1 megahertz
Yeah.
to
100
hundreds. Okay. And now the which frequency is going to see deepest?
The lowest frequency.
Yeah. So let's look at 1 megahertz. Okay. And now, do you know what approximate conductivity would be?
It's about 0.2 siemens per meter.
So conductivity 0.2 siemens per meter, so 5 ohm meters. Okay, so let's just set that up and see what happens. So those are the parameters that you could work with, and we could put in. We could even start that we've got no dielectric constant. Let's just start that epsilon is equal to 1. Okay, we can make that larger, smaller. See what happens. But let's just go ahead and use this. So the diagram that I showed you before was actually something that looked like this. So what we've got plotted up here is the skin depth, so that's in meters, as a function of frequency. So this goes from 10 to the 5th hertz
to 10 to the 10th hertz. 10 to the 5th hertz is kind of getting on that upper limit of where we usually are with respect to our quasi-static. So all of these airborne systems and that, but we saw that we could get maybe down to a microsecond, so that's equivalent of like 10 to the 6th. But the GPR systems, I'm not sure that I even mentioned that, but this is actually a pretty low GPR system, 25, 50 megahertz up to them. The other thing I didn't mention, I should have, is that they list a frequency for the GPR system. So if they'll say, okay, I've got a 50 megahertz system, right? So that's a 50 megahertz system. But if you actually looked at, so here's your amplitude. If you looked at the spectrum around there, they've really got, that's more like a central frequency. They've got a band around there, and then as you probably aware from seismic work, if you did the Fourier transform of this guy, you actually end up with maybe something like that. So the width of this is inversely proportional to the compactness of the wavelet. So a 50 hertz or 50 megahertz antenna has really got a source term that's a spectrum like this, and it's got a wavelet that's something like this. And then this thing is going to propagate down. That's the equivalent of your seismic wavelet. It propagates down every time it's reflected. That thing comes back. Okay, where was I? The other thing I wanted to mention was that in this curve here, so we got skin depth, okay, is decreasing logarithmically, okay, as a function of frequency. So remember the skin depth delta it's 500 root rho upon that. So it's the square root of frequency. So if you look on a log plot, okay, you've got one decade of change of skin depth is going to be equal to 2 decades of change of frequency, right? So it's going to have a slope of a half. In the low frequencies, as you go from, like 1 hertz up to 10 to the 5th, this curve kind of continues on a straight line like that. So it behaves this particular form here. As we get to that point where omega epsilon upon sigma, as long as this is much less than 1, then you're in that quasi-static region. Once this gets to be greater than 1, then you're in that really wave propagation. But the thing is, you still can't get around the fact that your waves still have to are following at least this skin depth rule. And if once you get down to that particular depth, then it can propagate as a wave. But there's no getting you away from the fact that you're losing amplitude because of this EM attenuation. So let's just take a look at this. So if it's 1 megahertz, so that's 10 to the frequency is 10 to the 6th, and up here, then the skin depth of that in, I didn't change it. So what did we want? We wanted, so,
What's 0.2 Siemens per meter, the log.
Minus 0.7.
Minus point. I'm so surprised.
And
You built it, you should be. Like, oh, why is that working?
Did you want epsilon at 9?
Oh, 1 epsilon 0, or 1. Okay, so this is where we are at 10 to the 6th hertz. Your skin depth for 0.2 Siemens per meter is sort of in the order of 1 meter. Okay, so that's your skin depth. And if if you're looking 50 meters down, okay, 50 meters down, that means that you're 50 skin depths, which means that you're e to the minus 50, which is kind of a small number. Let's see how the dielectric constant helps that. So instead of 1, let's make it. Not sure what kind of rocks are they? Did you say?
Sandstone, yeah, the dielectric constant
Costs about 4, about 9. Perfect. That changes things. Changes things a bit. Now 10 to the 6th, maybe it doesn't change it very much at all. You're still in the order of 1. If you start to get out towards 10 to the 8th, then you really start losing the effects of the skin depth. But the skin depth, or the EM attenuation, but the skin depth at that point is only 10 centimeters. So I would say that given the situation that you've just talked about here, that you're not going to see down very far. And you're talking about 900 meters?
No, about 1,000 feet, so 300 meters.
300 meters. Yeah, that's a lot. Anyway, so this is kind of a nice app. You kind of get a sense of, like, if I had a particular conductivity and dielectric constant, what is the skin depth going to be? And for any of these, 1 to 100 megahertz, you're still really much more geared to the EM attenuation and EM skin depth, unless you start to get really resistant. If I make this conductivity really small, okay, so if I made it at 10 to the minus 4, so it's like 10,000 ohm meters. Now at 10 to the at a frequency of 10 to the 6th, okay, then this is 200. So now at 10 to the 6th, I can see down. Well, I'm not sure what the other scale is here, but it's probably like 180 meters or something like that. So you might be able to. The bottom line here is you might be able to see a couple hundred meters down if it's really resistive. 10 to the 4th, 10 to the 5th ohm meters, which of course is why it works so well in ice, right? Because ice is really, it's a very strong resistor, and so the waves can go right through ice and reflect off of the bottom.
Yeah, so what we see from their received signal is they basically attenuate to certain depths, maybe let's say 50 meters. and then the amplitude doesn't change, it's kind of constant. So.
Yeah, zero is a pretty nice constant.
No, I mean, we still have some kind of amplitude, but it's not kind of follow that exponential decay. So, so you mentioned, I think like yesterday or when you talk about the MT, you said when you show that figure, so originally it kind of decay exponentially, and then to a certain point, it does not follow that trend anymore. It gets, the slope gets smaller, like it kind of attenuates small. You say it's because of like reflection from like.
No, maybe we should bring up that MT. Yeah. Yeah, just that.
When you talk about MT, you talk about Darwin attenuation.
But I think that that's geometric, like that's a geometric attenuation.
If it's propagating into the Earth, I never intended to say that it didn't follow an exponential decrease. As this wave is propagating in, it is always decaying according to the skin depth rules.
Yeah, I think that because in the beginning we kind of start from control source 1 over R cubed decay, and then go back and forth, and then MT sort of like. We overcome that, like to see deeper. I think she's mentioning the geometric decay. That's different. Yeah.
I see. Right. Okay. So maybe that was. So maybe, sorry, Ken, so maybe it was this thing here. So remember I said, okay, if we're talking about control source, so this is when we're introducing.
Yeah.
So I said, oh, this thing is falling off as 1 over R cubed here. And it falls off as 1 over R cubed here. So that's a 1 over R to the 6th.
Right.
And I said, oh, well, we could get rid of this geometric decay if we just had a plane wave that's coming down, right? Okay, so that's fine. We do that, but this plane wave will still decay according to skin depth rules as it's going down through. We can't overcome that.
Okay, so that's from the CSEM. I think that's slide number 66. Oh, that's good. So that's in the ground wave source.
Okay.
So on slide number 66.
Might be that's gonna clarify.
Yeah. So just kind of clarify this. We always have 2 types of attenuation, right? So we've got geometrical spreading, okay? That's what this 1 over R cubed is.
Right.
Because your field, varies as, M over R cubed and then something, right? So there's always this.
Yeah.
In addition to that, just as we're talking about with the inductive source, that as the waves go in, they're attenuating according to this approximately it's sort of skin depth rule. So there's always 2 things that are happening. And remember in the control source EM for the ocean, oh yeah. If that's what you're talking about.
Yeah.
So here we have
it falling off. So this is basically EM attenuation in the water.
Yeah.
In fact, if we just looked at, so this one's kind of coming down and then it kinks and it does that, right? Or, if we just looked at the geometric decay of the dipole, then that actually kind of it's sort of like this. So this is sort of like the 1 over r cubed, and then this is kind of composite of 1 over r cubed and the attenuation that's going on. Okay, so that's fine. Okay, now your next question.
So basically, I remember when we talked about this slide, you said, so basically you see that there's a kind of a change in the
Yeah, there's this kink
point.
here, right?
Yeah.
That's
Right.
that's okay.
Yeah. So this is the wave. This is the wave that has. So we've got our transmitter here, and then this part here is what we're seeing is the stuff that has gone here, here, and through our cold seam. So that's all this part. But then we also had waves that diffused up here, and then they went over like this.
Right.
So that's it. That's this part, right? So it's,
Right.
right.
Yeah.
So
Okay, so it's because of the air.
yeah. So that's energy that is what's coming. This part here is energy that's coming through a different path, and
So I'm thinking like in the ground penetration radar system, if we see the kind of the amplitude kind of decline, and then it gets kind of the
oh, I see, kind of flat.
yeah. So why? So I just want to try.
There could be standing waves coming, like if you got a source here and the surface here, like there could be standing waves, like going back and forth, right? So probably,
You still get decay.
yeah, so I think,
If you're up and down, you can
Yeah.
Do you, with the MT?
Oh yeah, that empty app. Sorry. Was that over?
Was this one you had in mind?
Yeah. So I'm maybe this helped. I don't know. We didn't show this app, so it's the flexibility here is that you can span a diverse set of frequencies. So there's a minimum frequency and a maximum frequency, and then there is a layer. So we could have, so this is air. So that's air. And then there's a layer 1, layer 2, and then a half space. So in this case, it's 10 or 100,000 and 10. And then what you're going to see here as we show this is the waves that come down, and then we'll see how they propagate inside here. But depending upon what the frequency is, the skin depth might be that the overall amplitude of this wave has, basically died out by the time it hits this layer here, or maybe it goes down deeper. So we can just sort of experiment and see visually what happens. And you can change also not only the resistivities of the layers and the thicknesses, but you can also change all of the physical properties. So you can change sigma and mu and epsilon. And you notice that those all came into play in Maxwell's equations. So this is kind of nice. Like, okay, what happens if I have, what's the effect of magnetic permeability, for instance, on electromagnetic wave that's coming in? Because in this formula for delta, was, 2 over mu sigma omega. So that was really the formula for delta. We sort of got rid of some of these constants, especially just basically said mu is equal to mu naught, but that formula for 500 root rho upon f, okay, is, well, this is better, let's put 1 over sigma f. Okay, so this was omega, so that's 2 pi f. There's the sigma, and the mu we said was mu naught, which was a 4 pi times 10 to the minus 7 or something. So you put all of those coefficients in, then we end up with a simple formula. That's the one to remember because it's just so simple. Right. So, but there is, if you change mu, then you see this, and if you change epsilon, then you've got this other term that can come in. So you've got electric displacement. So in this case here, with these fields, so here's the apparent resistivity curve, which is what you kind of initially at the high frequencies, you're just seeing this upper region. At intermediate frequencies, you're starting to sense this 1,000 ohms, so it's going up. And then for very low frequencies, you're just sensitive to the overall bottom structure. But the, let's see, how do we run the movie?
It doesn't run on here.
Yeah, it's not moving.
Oh, I
You can
see.
show in the.
Do you want to pull it up?
Yeah, this is kind of interesting to show you what those outlines are, because the waves are coming in, they're coming in like this, right? And then as they go in, sometimes they're positive, sometimes they're negative. So there's an envelope there that these are in, and that if you plot the, that is the outside of that envelope, then that has got the decay of this guy.
So,
What's the up and down going component? What did we want to show? This probably. So there's a lot going on here.
Yeah, so what you're looking at is an Earth with these properties. So here's a magnetic field that's coming in. So it's coming in, it's oscillating, and then it gets transmitted into the ground, and the moment it gets into the ground, it starts to, it's propagating down, but it's losing altitude, and by the time it gets down to, this distance here, it's pretty much decayed. And then if you change the frequency of this, then you get deeper penetration. If you change the conductivity of this, if you reduce it, it'll go deeper. If you increase it, it goes shallower.
okay. So like the one on the right is at a frequency of about 20 kilohertz.
Yep. So
I'm looking at, so basically after a certain point, you don't see.
Yeah.
So I try to read from the y-axis the depths, whereas that's about 1,000 meters. Where you don't.
Yeah, so here, that looks like about 1,500 meters. Well, let's see if that comes out all right.
But that's 0.1 milliseconds per meter. So it's quite resistant.
Okay. I
So
thought
it's about 10,000.
Okay.
10,000.
Let's just see. So rho on F. So what frequency do you? So we've got 500. 2 times 10 to the 4, and
Rho is 10 to the 4.
rho is
10 to the 4.
10 to the 4. So those cancel, so you get 500 over root 2, so that's about 300 meters as far as the skin depth. Did we do that right?
7. I think that's quite close, I guess. Depends upon where you pin.
If you look at the amplitude, so this conduct isn't necessarily going to be where it's like completely cut off, right? If you look at the amplitude and we decay by a factor of 1 over.
Oh, yeah.
Probably
Yeah,
in ballpark.
Yeah. So if you're here and then you go down to a third, so that puts it here. So that's this point here. Probably close.
Yeah, so like by two skin depths.
By 2 skin depths be 600 meters. So that would be someplace up in here. Yeah, that looks pretty close.
Yeah.
Anyway, those are things you kind of play around with, and you look at them, you visualize, and like, oh, okay, all kind of makes sense. And then I like exactly what you're doing. You're kind of thinking, you're cross-checking, and like, well, if this happens, then shouldn't we see this here? And then if we have to find some way of deciding, oh, okay, that does check, or wait a minute, that doesn't seem quite right. Always, then that's where you learn from. Thank you. I appreciate that. Okay. So it's Friday. You've been listening to all this stuff for 4 days. There's a couple of more things that we have, but maybe it's it's a little bit more at this point that you really want to hear. At the same time, I at least want to present it. I don't want to present it in detail, but I want to show you that this material exists. If at some point it's of interest, then that's great. But I don't think we want to really kind of go through things in too detail. But I'm just going to kind of slip through and tell you some of the things, because they are really important in particular circumstances. And so, just to be aware that here's a problem that can be useful. So the first thing I wanted to do is talk about EM and IP inversion, or sometimes it's called EM decoupling. And this is actually what Sagi has just written his thesis on. And so he's done some really nice work. Could get a chance just to kind of show you the highlights. And then there's a case history from that kimberlite deposit that I was talking about, Please quiet show. I did mention this just briefly yesterday or the day before, and now perhaps it becomes a bit more important because we've just done the IP. So when we were just talking this morning about the IP, we said, oh, well, we put the current on, and then we turn the current off, and then we get this decay of these secondary charges, right? And so we were looking at this kind of a scenario. So here's the current, and then here's my voltage, up like this, and then I turn it off and it goes down, and then I said, oh, now we get this nice decay, and we use this as our IP response, and we're good to go. Okay? This is what happens if you're all at DC. However, we spent 2 days here talking about electromagnetic induction and saying, well, if we turn the current off, now we're going to have a lot of induced currents in the earth, and we haven't talked about those here. If the earth was not chargeable, but was only conductive, then what I would see from that is that I would turn this is the magnetic field, I'm going to turn that current off, and I'm going to have a decay that kind of looks like that. So my voltage that I measure in my coil is actually going to have something that looks like that. So in fact, when we do this, we have 2 things going on. we've got our IP charges being built up. We have superposed on that, something else that really is the EM part of that. So that creates a mess because the IP could be contaminating this EM signal, or the EM could be contaminating the IP, and it kind of depends what you're interested in. If you're interested in the IP signal, then there will be a time in which the EM part has decayed away and you can just measure that IP signal. If you're interested in the EM, then you need to worry about whether there's some effect of the IP. So you need to kind of somehow decouple this, and really that's what Sagi was doing for his PhD. And from the point of view of the IP, usually these early time signals, just because they're confused, they're contaminated with EM effects, they just throw them away. But what we were able to show is that you could actually keep these signals, invert them in terms of a real time domain EM experiment, that get a conductivity from that, and then help use that to basically decouple the EM and the IP effects. So that was really the Microsoft is updating me. Okay, so it's that whole process, realizing that the moment that we turn currents off, we got two things happening, and that you might want to have to work a bit to kind of separate these things out and try to decide whether you're looking at an EM induction effect and you want to get conductivity, or whether you're trying to do IP effect. So I think, yeah, maybe that's all we need to do. Actually, I might make one comment. Before, if we're just thinking about this as a DC resistivity experiment, we could take these times here, those late times, and then we could just go ahead and invert them to get the conductivity. That's what we do for the DC. In this, if we take early times, it turns out that the early times are so big compared to any IP signal that you can really think of this as a time domain EM survey. And then you could take the time channels that are associated with this, invert them just the way that we did on Tuesday and Wednesday, and come up with a conductivity structure. So that's the advance there. And then once we have that conductivity structure, we can get rid of EM induction in those later times, get pure IP signals. Then we can go ahead and invert just as we've shown you up. So that's basically the gist of that. The other advance, and this is where Sagi gets really top stars, is that you can also do IP surveys from inductive sources. So here's the idea. If ordinarily we've got some kind of a grounded source, here's our current, and we put on, here's our block of interest. And as the current goes through here, we gradually build up the charges, and we can measure those charges here with the voltage. So this is where we were before, voltage goes up like that, and then kind of phase, we measure these guys. The charges that are built up, all these positive charges here, negative charges here, those things that are built up, they're built up because there's a driving force through here. So there's an electric field that's on here, and that continually is pushing these guys like this, and then gradually builds up to equilibrium. That's what we saw. And then we go ahead and measure it. Okay. If you change this to an inductive source, however, the physics changes, the situation changes a bit, because remember, if we had a loop here of current, if we have some body that's sort of sitting out here, and if we have a current in the loop that we just simply turn off, then initially there's no currents through here, right? So there's not going to be any charges being built up. We only get charges being built up when there's actually a current flowing. That's it. The current flowing through a rock in order for charges to get built up. In this situation here, we now kind of understand what's happened. The moment that we turn this thing off, there's currents in the earth, but they're sort of sitting up here. So they're not affecting this. A little bit later, however, the currents, there will be some currents that are flowing through. And the moment that you get those currents through, now we're going to get charges being built up. And then later on, the currents kind of diffuse through, and then there's nothing left. So if you look at some point in here, inside the rock, you find that the currents that are flowing through here, are non-existent. Then so this time they're non-existent, and then they gradually reach some kind of maximum, and then they decay away. So it's only during this time here that you could get these charges being built up. But if that's long enough, then there might be some charge accumulation, and then when those charges disperse back, they actually give rise to magnetic fields that could be measured. So that's the whole idea of the inductive source IP, is that you have a source that is, it's inducing currents in the earth. You've got something in here which charges up only when there is currents, and then when it discharges, you're actually not measuring the electric fields, okay? But you're measuring current, the magnetic fields that come from the currents. Because if you thought about this thing being charged up, then there's positive currents here, or positive charges here, negative charges here. So there's like currents that are flowing like this in the earth. As those discharge, then there's still, there's these secondary currents that are flowing around, and they actually give rise to a magnetic field that you can observe. So this is all pretty new stuff, and has a number of applications, not only in mineral geophysics, but also in environmental groundwater issues, things like that. And the group at UBC took on the challenge of looking at geophysical data from over these some kimberlite pipes, in which we actually used multiple types of surveys, different kinds of frequency and time domain airborne systems, and also looked at the IP signals from that and tried to put together a rock model. So we first of all inverted for three-dimensional properties of different physical properties of density, magnetic susceptibility, electrical conductivity, and chargeability, and then did some statistical clustering to decide, okay, which rock or which groupings of physical properties would constitute a rock,
and ended up with a rock model a geophysical rock model that looks like this. And that was actually then compared with a rock model from drilling, which kind of looked. So there was a lot of steps in there, but the big things were that able to take an airborne time domain system, extract the IP signal from that from the measured data, invert those IP data, and come up with chargeability that's reflective of what's happening for different types of rocks, and then put it together to get a rock model. I think that's, yeah. Actually, let me just, there's a few things here that actually really might be of interest. So I'll still just put it back into context. So here's an area that we're dealing with. It's in the Northwest Territories. I showed you this picture before. So those are two kimberlite pipes. So a kimberlite pipe looks like this. It's an explosive event that comes from depth. They're very often characterized by having a lake up top, because things have been ejected into the atmosphere, and then you've got this kind of big hole, kind of collapses in on itself. And then there's a number of different rocks here. They all have a K after them, which means kimberlite. So that's a pyroclastic, that's a volcanic clastic, hypabyssal. It's just geologic names of rocks. There were many time domain or many airborne data sets that were acquired over here. There was a frequency domain data set. It's a DIGEM system. So it's kind of like the resolve system. So it's kind of coplanar coils. And then there was an airborne system in 2003, a VTEM system in 2004, and then there was actually a ground nanotem system. So all of these are time domain systems. What's of interest here is the time domain curve. The sounding at, let's say at this particular location here, sort of sitting here, is positive, and then it goes negative and have something that looks like this. So what we're seeing here is, we're kind of changing polarities on here just so that things are meaningful, but the response of of a time domain system should really give on a log plot something that's kind of positive and decays with time. So here's time, and here's our response. So that's kind of what we would expect to see if the ground was just conductive. And out of the characteristics of this decay curve, we've tried to extract from it. In some cases, however, the curve looks more like this. It can start off positive, and then it goes negative, like this, and then back here. If you have a coincident transmitter and receiver, it's shown mathematically that the only way you can get these negative values is if there was an IP effect. So this was a big thing from the point of view of airborne geophysics, because people would see these, what they called negative transients, and they were trying to figure out what the heck are they. And initially they thought, well, it's just the instruments, they're just giving up crappy data. But then it was repeatable, different instruments came around, and they kept measuring the same thing, and they realized, like, okay, that is a signal, direct signal,
that is related to IP responses. So people have now been concentrating on these negative transients and trying to see what happens. Now, what we notice in here is that at this DO27, it starts positive, which is fine, and then the dashed lines indicate that it's negative. So there is something chargeable there. And at this upper kimberlite pipe here, things are so chargeable that really the only thing that you see is some negative values. So it's really a lot of chargeability. So that was an interesting challenge then of trying to figure out, okay, what to do with that. Within the concept of inverting for chargeability, we need to have a conductivity structure. And in this case, the DigIM data and the time domain data were combined, and they gave us a 3D conductivity model. In plan view, you see there's a big conductor here, a smaller conductor here. And in cross section, that's up here, there's a conductor, it goes to the top, and here it's buried. So that gives us our conductivity. However we're going to work with chargeability, we always need to know conductivity. So that gives us that. And then the idea about how to work with some of these problems in the intermediate. So let's suppose we just look at time. So the IP signal, if we didn't have any induction effects, should be, well, which way do I want to plot it? No, let's do it like this. So let's plot time in here. And if we look at very early times, so at very early times, then we would have basically EM induction responses happening. The IP, even though it might exist, is so small we just don't see it. So there's a region here at early times where we just have pure EM effects, and there's a region at later times when we just have IP effects, all of the EM parts of. But there is a region in between where things are confused and you have both of them together, and so you have to try to figure out what to do. The procedure is to find, first of all, an electrical conductivity, and that could be done by inverting these early time channels. And then we forward model that with Maxwell's equations to get an EM response. And then we subtract that EM response from the observations to give the IP response. So this process is called EM decoupling. We're getting rid of the EM response. And what I want to show you here, and this was actually quite dramatic, is that here's the observed data at a particular time channel, 130 microseconds. We got the conductivity and then predicted what the response would be. And now we subtract this from the observations, and we're left with an IP signal that looks like this. So these are now the data that should be inverted. That's the stuff that you're looking for. So you see most of this stuff is just completely gone. And if you look at a slightly later time, at 400, so again, this is our observed. These are the predicted values from the conductivity, and we subtract those, end up with that. So this is huge, right? This is like a major first order change. That was the image that you had before. Now you make these corrections, and you get these data here, which now you're going to go ahead and invert them. So that's done. The early the early times, 130 microseconds. You invert those data in 3D. You see a chargeable block up here, some chargeable bodies here, cross section, they look like that. And at later time, the situation is different. We've got two chargeable bodies. This body down here is more chargeable than this one up here. So there's something very different about the rocks and the rate that they decay. So bodies will charge up, and then they effectively decay at perhaps e to the minus some t upon tau with some time constant. So some rocks decay really quickly, and others decay slowly. So if you could distinguish between something that has a slow decay and something that has a fast decay, then you've got two different rocks. And that's clearly what we're seeing here, because we've got very large differences in the structure of these guys. If we look at the representation of these complex conductivities, there is a formula. There's many ways of describing dispersive characteristics of rocks. This one's a something called coal representation. It's got a few parameters. There's tau, that's the decay constant. There's a C up here, which is telling about the frequency dependence of things. The main thing here is really sort of what the chargeability and the decay constant is. And if you do all the inversion analysis and you look to see what the best estimates of eta and tau are, you see that various rocks here are grouping in different regions. So there's a group of rocks that are red that have this sort of tau and eta, and they're very distinct from green rocks over here. So these rocks in green are very distinct from things that are in red. So it's a different, must be a different geologic unit. So the final data integration was to take gravity data obtained from the air, so it's airborne gravity, and airborne magnetics. Those were each inverted separately to give a 3D density and magnetic susceptibility model. There was frequency and time domain data that were inverted, and everything was then put together to get these different physical property models, including an early time chargeability and the late time chargeability. And then you now take these and then you cluster and you try to find a rock. Let's find a rock that's high density, low susceptibility, high conductivity, high early time chargeability, and low late time chargeability. Some arbitrary representation. So you could use clustering analysis to find different configurations of these. And now we come back to the picture that I was showing you before. From doing that analysis, ended up with 5 different geophysical rock units. So these are just different clusterings. And then when that was compared to the drilling, and there was substantial amounts here, these are actually the rock units from drilling. So it came up. So that was a very big effort on the part of the UBC group, and then we published that in a sequence of 3 papers in geophysics in the case histories. Okay, so that's that kind of brings us through all of these major items, and we're a little bit earlier. We have options. We could either leave for lunch now and then come back, or we could talk a little bit about your problems and do something. So I think going to lunch, I think that would be, this is probably a good time to take a break. So let's go for lunch, and then we'll come back, and Sergio and Tintin and anybody else can talk. And we'll do a few things with the apps, just talk a bit about the future. Here. Oh.